Hello there, Mr. Sutton here, bringing you this lesson on the law of sines. In this one, we're going to find missing sides and angles of triangles if we have two angles and a side, or two sides and an angle that is not between them. And for the real-life application, we're going to decide whether it's safe to cut down a tree. In order to help you properly meet the star of this lesson, I'm going to give you a Desmos link to go to here. So pause the video and go here, and while you're there, you're going to see a triangle. Move the vertices of the triangle and watch on the left how sine of A over A, sine of B over B, and sine of C over C change, and see what you can conclude about the ratio of an angle's sine and the side across from it or opposite from it within a given triangle. So here's the link. Here's our triangle, and we're going to start moving these vertices around. You can do it yourself or follow along with us. So over here on the left side, we've got these different fractions or decimals changing as we move these vertices. All right, let's move another vertex. Now I'm getting all sorts of different triangles out of this, all sorts of different angles. I'm going to make my triangle look all crazy and obtuse like this. What is happening to those numbers? Well, we've got 0.049, 0.049, 0.049. So, and then they're changing as you make your triangle look different. But what do you notice about them all with respect to each other? Yeah, that's right. I mean, give or take a few crazy decimals, several steps down the way, these are essentially the same number. So every triangle has kind of a special sine over side ratio within that triangle that's the same no matter which angle and side you're looking at. In general, then, we can conclude, and this is the law of sines here, we can conclude that sine of A over A is going to give us the same ratio as sine of B over B, which will also equal sine of C over C. So this gives us a formula we can use now to find sides and angles in non-right triangles. What do we need to do to make this happen? So here's the catch. We need an angle-side pair that are across from each other to make this work, and we also need the side or angle across from our missing piece. So two situations here. We have an angle-side pair and the angle across from the side that we want. So if you go in order here, we could call this angle-angle-side. Or another situation, we have a side angle pair and we have the side across from the angle that we want. So side, side, angle. But as long as you have one of these two situations, you can use the law of sines. And you'll notice that we don't really need all three of these. We really just use two of them. It's really just a proportion that we're setting up here between one angle side pair and another. The catch is we're not using the angle, we're using the sine of the angle. Before we go ahead and actually use law of sines to find some sides and angles, we're going to talk about that side-side angle case, which we call the ambiguous case. And here's why. So let's say we only know angle A and sides A and B. In these following situations here, there's actually three possible cases for what we could be dealing with. Possibility number one is that the side A here across from angle A isn't quite long enough to form a complete triangle, so then we actually have a triangle that doesn't exist. And this does happen sometimes when you do your law of sines math out. Another possibility is that we have one side of length A, and we only have one angle B, and that's it. There's just one triangle that meets this condition. And the other possibility is that that side A might give us not one, but two different triangles, depending on which way it's swinging. So in this case, if you're trying to find this angle B here across from side B, there's two possibilities. One possibility is the original answer that you would get on your calculator, and another possibility is another angle. So what would this other angle look like? Well, this is the angle we're talking about here. This is our alternate angle B, and it would have the same angle as this angle here because this is an isosceles little triangle we've drawn in here. Now this angle, this is just on the same line as the first one. This would be 180 minus x. So this alternate angle would just be your original angle subtracted from 180. It would be the supplement to your original angle. So this is another possibility that we have to look out for. When we find an angle with law of sines, you have to subtract it from 180 and see if its supplement can also fit in the same triangle. And we'll have an example where we do that later. Now you might be wondering, why don't I have to go through this craziness when I'm doing SOHCAHTOA and I'm inverse signing something in that situation? We actually don't have this issue with right triangles, because if you subtract the right angle from 180, just because there's 180 degrees in a triangle, you only have 90 degrees to work with for the other two angles. So, I mean, let's say that one of your angles was 30, you subtract that from 180, 150 is not going to fit in a right triangle because you've already used up 90 degrees. So it's only with non-right triangles when you're trying to find angles with law of sines that we have this issue. Let's do an example now. In this one, we're trying to find this missing angle x, and we have a side-side angle situation here. To put it another way, we have a side angle pair across from each other, and the angle that we want is across from a side that we know. So in this side-side angle situation, we use law of sines, which again, I'm only going to write the first two parts of that. I don't need sine c over c. And now I'm going to plug in my numbers. So for one of these, I have to have the side angle pair that I know about. So we could say, for example, sine of 57 degrees over 17. And for the other one, I just have the other angle side pair, so sine of x over 13. So for this one, I'm going to go ahead and at least get sine of x by itself. I can do that by multiplying both sides by 13. I don't have to cross multiply because multiplying by 13 will take care of this. So I've got sine of x equals 13 sine of 57 degrees over 17. And now I have to do inverse sine of all this stuff to figure out that angle. Now, when you do this, I mean, you could get the decimal and then inverse sine it, or you could just do inverse sine of all of this at once. I'll show you that awesomeness on the calculator now. So I'm going to do second sine, so sine inverse, and I'll put this whole fraction in here. Now, I'm going to use my cool fraction formatting on the newer 84s. So if you do alpha y equals and do this n over d, you can set up a real fraction bar. So I've got 13 sine of 57, and I'll close that parentheses. And down here we've got 17. And now I'll just close the parentheses, and we get 39.9 degrees if we round off. Now we said that when you get an angle using law of sines, you have to go ahead and subtract it from 180 to get the other possibility. So 180 minus 39.9, that's going to be a little bit more than 140, so 140.1 degrees. Now we're not done. Just because this is a possibility doesn't mean it can actually exist. You always have to check to see if your alternate angle actually adds up to 180 or more with the angle that they already gave you. We need to see if this angle fits inside the triangle that we started with. 140.1 plus 57, is that going to fit inside a triangle? It is not. That is bigger than 180 degrees. So we have to cross off this answer, and we actually only have one angle that this comes out to, so this is only one possible triangle that we have for this situation. Here's another problem. Pause the video and try this one out on your own. All right, so law of sines again, because we have an angle side pair that we know that are across from each other. So here it is. We can write sine of 31 over 21.7 equals sine of x over 25.3. Multiply both sides by 25.3 to isolate sine of x. And then let's use inverse sine to figure this out. So I've plugged all that into my calculator here. Inverse sine of all this stuff gives us 36.9 degrees. And again, because this is a non-right triangle, we also have to find the quadrant 2 version of this. So 180 minus 36.9, that's going to be 143.1 degrees. Yep. And then can that fit in the triangle with the angle they already gave us? Well, the angle they gave us was 31 degrees. If you add that with 143.1, it's going to be less than 180, so we definitely can fit those in the same triangle. What this means is that we have two answers, 36.9 degrees and 143.1 degrees, that are both good, acceptable answers. We don't have enough information to choose one or the other, so we're just going to use both. Here's one more missing angle problem that is clearly a law of sines problem. Pause the video and try this last one out on your own. So again, law of sines. So we can write sine of 141 over 14 equals sine of x over 33. Multiply by 33 to get sine of x by itself. And let's take inverse sine of all that now. And let's see what the calculator has cooked up for us here. Ooh, that's no good. What happened there? We got an error. So we entered it correctly. The problem here is that they gave us a bad triangle. So this is a no solution. It's not actually a real triangle. Notice that this is not drawn to scale. That doesn't necessarily mean it's a bad triangle, but look what they did here. I mean, 141 degrees, that's definitely not what 141 degrees looks like. So if they're not required to draw a triangle to scale, you sometimes will get these triangles that are kind of phonies that you have to figure out by doing inverse sine. We're going to wrap things up with a real-life problem. A severe storm leaves a tree in your backyard on its last limb. Get it? Limb? The tree is leaning at a 70-degree angle. You stand near your house, which is 30 feet from the tree, and measure a 52-degree angle of elevation to the top of the tree. If you cut down the tree in the direction it's leaning, will it fall on your house? So in order to answer this question, we need to know the length of the tree. We'll call this x here. So how do we figure this out? Pause the video and see if you can puzzle that out on your own. All right, let's see what we came up with here. Now we know that the x side that we're looking for is across from an angle that we know, 52 degrees. But you might be saying, wait, Mr. Sutton, we don't know the angle across from the only side that we actually do know, this 30 feet. We don't know this angle up here. Oh, but don't we? We know that the angles in a triangle add up to 180, so what's the missing angle here going to be? Well, it's whatever 180 minus 70 plus 52 is. So let's see, that's 122 that we're subtracting, so 58 degrees for this last angle. So now that we've got that, we can in fact use law of sines. We can say sine of 58 over 30 equals sine of 52 over that x side that we're looking for. And now the algebra is a little bit different because we're looking for a missing side, not a missing angle. Probably the fastest way to do this algebraically is to multiply, or actually just switch x and sine of 58, so move sine of 58 down here, and then multiply both sides by 30. Basically cross multiply, but then divide by sine of 58. And let's plug this into our calculator. So we've got sine of 30 times sine of 52 divided by sine of 58. Calculator says that is going to be 27.9 feet for this real-life problem. So does that mean our house is safe? Because, I mean, this is less than 30 feet. But hold on a second. All the problems we've seen today, except for the one that had no answer, right? We had to test to see if it had an alternate solution. Do we have to do that here? It turns out we do not. When you're dealing with sides, you only have one solution. Really, the only reason we had that two-solution weirdness was because of the way that angles work in the unit circle, with sine being positive in both quadrants 1 and 2. We don't worry about any of that when dealing with sides. So this is our only answer. That means we can chop that tree down. Timber! Woohoo! Our house is safe, the tree is down, and this lesson is just about over. So, just a little public service announcement. Make sure your homeowner's insurance is paid up and hire a professional before using the power of trigonometry to chop down trees. Until next time, this is Mr. Sutton signing off.